hope you have faced your semester examinations properly. Now, I again welcome back to our classes on approximation methods. We have already finished our discussion on the first approximation method coming under the category of stationary problems, that is the versatile perturbation theory. Now we move on to another approximation method suitable for, once again, stationary problems or time independent problems, which is the classical variational method. This is a mathematical procedure that you have already discussed in different branches of physics, particularly with a wide extent in classical mechanics, while deriving the equations of motions in classical mechanics. Here we will make use of the theory as a suitable approximation method in quantum mechanics, where the other approximation methods like perturbation theory or the upcoming WKB approximation fails. Variational method in quantum mechanics. It's a very well known fact that dynamical equations in physics are derivable from a suitable variational procedure or a variational method. This we have used in the case of the derivation of the equations of motion in classical mechanics following Lagrange's equation or Hamilton's equations of motion from the variational procedure referred to as the Hamilton's principle of least action. The Lagrangian equation is, I hope you will be able to recall that it has been derived from the Hamilton's principle of least action. Whenever a classical object is performing a dynamics, the action integral will be an extremum. The statement is like this, and from the mathematical principle corresponding to the extremum of action integral, delta variation of Lagrangian q dot t dv or dq dp dt q dot dq dot dt will be equal to 0. This is the Hamilton's principle of least action. The action integral will be an extremum whenever an object is performing a dynamics. Based on this principle, you have derived the Lagrange's equation of motion. Another very classical usage of the variational method in physics is the derivations of different equations and principles coming under geometrical optics or the so-called ray optics from Fermat's principle of least time. The principle is like this: a ray of light will correspond to that path for which the time taken is an extremum. It is from this variational principle, so definitely delta variation of time taken by a ray of light in traveling from one point to another through even a set of medium, the set of media will be an extremum, or mathematically delta time taken delta t will be equal to 0. It is from this variational principle or extremum principle you have derived the various principles in geometrical optics that involve the fundamental laws of reflection, fundamental laws of refraction, etc. And I must tell you that this variational method is possible in quantum mechanics also, because in quantum mechanics also basically we are going behind dynamical equations, say followed by quantum mechanical objects or microscopic objects. Then whether these are derivable from a variational method, that is the basic fundamental question which we will be addressing as long as the applicability of variational method as an approximation procedure in quantum mechanics is concerned. Yeah, it is applicable, and the applicability will be limited to the systems with non-Hamiltonians. Though the Hamiltonians are known, we are absolutely ignorant about the wave functions, wave vectors and eigenvalues corresponding to that Hamiltonian, or say corresponding to the system under our study. And generally this method is a choice when you cannot, I have a spelling mistake here, I think cannot, I might have written can't. the problem cannot be solved exactly or by perturbation or by applying perturbation procedure. And generally, once again, the variational method give you an upper bound value for the eigenenergies. So there is an approximation, an accuracy issue that might be always encountered other than when the approximation method is applied to quantum states other than the ground state. So generally this gives you a better approximation for the ground state energy, and even in that case this gives you an upper bound value for the eigenenergy also for the ground state. And for excited states as well, this method is applicable, but the accuracy will be generally questioned or questionable. Here also you can expect a question about the validity of the approximation method under the title variational method. There is no such a correct validity, but often a question like that arises, or you'll have to face such a question almost often in the question papers. So this is an approximation method suitable for those problems whose Hamiltonians are well known, but their eigenvectors and eigenvalues are not known. This generally give you an upper limit for the eigenenergies, and is a method suitable for the evaluation or most suitable for the evaluation of the ground state energy. There will be accuracy problems arising once you are going to apply the method for excited states. And generally the method is applied when you have no choice of applying other approximation methods like perturbation theory or WKB. Generally WKB is not included here because WKB will be limited to some problems that are to be treated as one step ahead of the classical problems. Now we will see the mathematical principle underlying variational method. This is not involved in your syllabus. This is in fact a brush up of what you have learned during your discussion in classical mechanics. I think in module number 3 in classical mechanics paper you have discussed variational principle in classical mechanics. Consider a mathematical function, say f, which is a function of alpha, where alpha are generally referred to as the adjustable parameters. Then the delta variation in alpha f corresponding to a small change in this independent variable alpha from alpha 0 to alpha may be represented as a delta f. Delta f, mathematically this is equal to f of alpha minus f of alpha 0, and this you can evaluate using Taylor series expansion as say dou f by dou alpha at alpha 0 into delta alpha plus dou square f by dou alpha square at alpha 0 into delta alpha whole square over 2 factorial plus etc etc. And this is nothing other than dou f by dou alpha at alpha 0 into delta alpha. And if f is having a stationary value, because you are making use of an extremum principle as long as the variational method is concerned, generally there will be a quantity and the dynamics of the system will be such that this quantity will be an extremum. An extremum, the phrase extremum is used in the sense that this quantity while the system is performing a dynamics will be either a maxima or a minima or will be having a stationary value. So mathematically we will be making use of this extremum principle that has only one meaning: the first derivative of this quantity will be equal to 0. If it is say a maxima or a minima, anyway whatever may it be, whether it is maxima or minima, the first derivative will be equated to 0. And for maxima and for minima, the second derivative will be different. Either this will be showing a negative value or a positive value. So this is the mathematical procedure that we will make use of under the title variational method. So what we do is that we have a function that is to be identified, which is such that when the system is performing a dynamics, this parameter or this quantity will be an extremum. Mathematically, this gives us the idea that the total derivative of this quantity with respect to its dependent variables or independent variables of the problem will be equated to 0. This gives you a mathematical procedure of evaluating this, say, quantity, say alpha, that are usually referred to as the variational, adjustable parameters. A knowledge of alpha will give you a method of evaluating f explicitly. And this evaluation of f is supposed to give us either the equation of motion that the system will be following or some valuable informations about the nature of the dynamics followed by the system. Then now let's see how this variational method is applied in quantum mechanics. In quantum mechanics, we will be making use of this approximation method under the title Rayleigh-Ritz variational method. There are some other variational methods also available. As per our syllabus, we will be talking about Rayleigh-Ritz method only. So, to apply the variational principle in quantum mechanics, we will have to first of all identify a quantity whose extremum will be strictly followed whenever the object is performing a dynamics. From the physical intuition on the concept of quantum mechanics, we can directly take this quantity as the energy eigenvalue, because corresponding to any particular quantum state, this is something known from the very beginning of wave mechanics or quantum mechanics. From the Bohr's theory, he stated that the orbit will be corresponding to, or say electron will be corresponding to certain orbits, and these orbits are corresponding to certain stationary energy levels, certain constant energy levels. So this energy value is to be an extremum as long as any quantum mechanical system is concerned, and the energy eigenvalue is often evaluated as the expectation value of the Hamiltonian. So the quantity whose extremum will generate the fundamental equation of motion in quantum mechanics might be the energy eigenvalue corresponding to each and every quantum state, or the expectation value of Hamiltonian, which is being evaluated from the fundamental principle of quantum mechanics as, say, expectation h equal to scalar product psi h psi divided by scalar product psi by psi itself, provided psi is not a normalized wave function. If psi is a normalized wave function, the denominator will be vanishing as it is equal to 1, and this is a ratio. So it is this quantity that is supposed to give us the dynamical equation of motion in quantum mechanics. If this statement is true, definitely we will be able to derive the fundamental equation of motion in quantum mechanics from the variation being applied to this particular equation, which here onwards we will be calling as the Rayleigh-Ritz variational formula. So the Rayleigh-Ritz variational formula is delta variation of this equation equal to 0. Of course, this is the expectation value of energy. Once you put delta E equal to 0 after stating this one, then this is referred to as the Rayleigh-Ritz formula or Rayleigh-Ritz variational formula. So we will prove that this variational method is applicable in the case of quantum mechanics as well. In order to prove that, we will have to derive the fundamental equation of motion in quantum mechanics by applying the variation to this expression for energy, or the concept that we have already done, as the fundamental equation of motion in quantum mechanics is derivable from this variational principle, for the variation of energy eigenvalue should give rise to the fundamental equation of motion in quantum mechanics, which is nothing other than the Schrodinger's equation. So we will now do this as a proof for the applicability of variational principle in quantum mechanics.